Hey everyone, welcome back. In this episode of Read AI with me, I'm going to be taking you guys walking down memory lane and look at this paper published by Yann LeCun in 1989. And this is particularly a good piece of memory for me in person because this is actually the first paper that I read about 4 years ago, and that's the first paper about neural network that I read in my entire career. So I would say that other than the online tutorials, the code, whatever sources that you can find online, reading the actual paper published by these original authors, it's of course the most rudimentary and authenticate way to learn about these methodologies. So with that being said, let's get started. The title of this paper is called Generalization and Neural Network Design Strategies. So right off the bat, I think the interesting thing to point out is the author is really trying to be flexible. At that time, Yann LeCun is actually not at NYU. He's at University of Toronto, Department of Computer Science, and I can tell from reading his paper that he already has some rudimentary idea that he wants to get into, and he actually had this field of artificial intelligence already in there, in his head, somewhere there that's established. And this paper is a reflection of one spot of what that field looks like 30 years later. So that's one of the reasons I found this paper amazing, which is because it's sort of like a small lens that allow the reader to really look into the lens and see what the field might be like. And this is 1989, so if he's a grandfather or founder of modern day artificial intelligence, I think he deserves full credit. I think this paper definitely defines the field. So let's get into it. Generalization and network design strategies. The first thing is obviously abstract. Okay, so let's take a look. An interesting property of connectedness system. Now that's not a word that we use today. Usually you would just say some sort of mapping or connection system. But hey, let's stay with it. Connectionist system is their ability to learn from examples. Although most recent work in the field concentrates reducing learning times, the most important feature of a learning machine is its generalization performance. It is usually accepted that good generalization performance on real-world problems cannot be achieved unless some a priori knowledge about the task is built into the system. And the keyword here, I think that this paper is really contribute to the literature is backpropagation. And specifically, I already read the paper, so I know a little bit of what it's talking about. It's really getting into the idea, the engineering way, the efficiency, the speed, trade-offs of backpropagation, specifically when it deals with the level of complexity of the design of these networks and the performance. So if you want to say that using modern day language, if you think that this is the beginning milestone of black box algorithm, I do believe this paper built the foundation of that idea. So let's take a look. The backpropagation networks provide a way specifying such knowledge by imposing constraints both on architecture and on its weight. In general, such constraints can be considered as particularly transformation of the parameter space. I like that language, Nowadays, we read these languages in textbook, but hey, 1989, if you can write that in a paper, I do believe it's groundbreaking. Building a constraint network for image recognition appears to be a feasible task. We describe a small handwritten digit recognition problem to show that even though the problem is linearly separable, single-layer networks exhibit poor generalization performance. Multi-layer constraint networks perform well on this task when organized in a hierarchical structure with shift invariant feature detectors. Okay, so right off the bat, they're trying to say, okay, there's a hidden trade-off here, right? There is perhaps I can draw a graph that's accuracy, or you can say performance, and then maybe that's one axis, and then another axis is the complexity and the design of the network. So here we're going to say complexity design of a network. So in other words, as complexity go up, right? So as you move right of this graph, the expectation is the performance get better, right? So you should be able to explore something like that. Or if you handle enough experiments, usually that's kind of the path that we expect, right? Higher the complexity, higher the performance. The lower the complexity, maybe poorer the performance. So I think that's going to be the graph that this paper is trying to show. So keep that in mind at the beginning of the paper. We're going to see some experiments later on. All right, so the connectionist architecture have drawn considerable attention in recent years, right? Nowadays, we talk about fully connected layer. I think in the old days, he used this word connectionist architecture. I'm not sure if people still use that today, but here, I think the importance is to recall fully connected layer. Maybe that's like a better keyword for you to keep in mind when you read the paper. Okay, among the numerous learning algorithms that have been proposed for complex connectionist networks, backprop is probably the most widespread. So first of all, the keyword backprop. Backprop was proposed by this guy, but had been developed before by several independent groups, blah, blah, blah. So this is just really to talk about the history, right? The citation. Where does this thing come from? Where's the math? I'm not going to bore you guys with that. I'm going to be jumping right in. Two performance measures should be considered when testing a learning algorithm, which is a speed and the generalization performance, right? So that's pretty much the graph that we draw. You can consider another axis to be speed, and then this is the performance. And then generalization is main property that should be solved. It determines the amount of data needed to train a system such that a correct response is produced when presented a pattern outside of the training set. That's a typo, right? Patterns is a plural form, so you can just say patterns. You don't need to say a. We will see that learning speed and generalization are closely related. Although various successful applications of backprop have been described in the literature, the conditions in which good generalization performance can be obtained are not understood. Considering backprop as a general learning rule that can be used as black box for a wide variety of problems is of course wishful thinking. He missed a period. Okay, so I think this black box is gonna be a buzzword here, at least for nowadays. And apparently, it's published in a paper in 1989. I don't know if this is the first time this concept is mentioned. Maybe somebody else had mentioned this before, but this is at least for me the first time I'm seeing this. So it's kind of important. Although some moderate-sized problems can be solved using unstructured networks, we cannot expect an unstructured network to generalize correctly on every problem. And then we move on to talk about this a priori knowledge of model building, right? If you're gonna have some sort of domain knowledge, you might have an a priori knowledge, and that can serve as like a North Star, right? It's like a guideline for you to build your model. Now that's gonna be a separate direction than generalization, right? If we're going to be talking about generalization, then the question we're really trying to answer is find one approach that perhaps works everywhere. That's a separate approach than relying on the prior knowledge. So I think the contribution here is really to break that barrier and to hit the area and get into the field of really generalized performance of one type of network architecture, and specifically later on we're going to be talking about a family of network architecture because there are lots of tuning parameters, layers, nodes, we can all change that. So let's keep going. Tailoring the network architecture to the task can be thought of as a way of reducing the size of the space of possible functions the network can generate without overly reducing its computational power. You missed another period. Maybe sometime during the rest of this paper, he just stopped using period. That could be a typo. It could be just the poor publishing framework that people were using in 1989. Okay, and then he cited a couple of studies to say that these previous studies have shown that the likelihood of correct generalization depends on the size of hypothesis space, uh, the size of solution space, and the number of training examples. I believe there's not a period. Okay, so I think these things are good things to keep in mind. I'm not going to bore you guys with, but I think these things are definitely good things to keep in mind, specifically when it gets into the tuning performance, the tuning process of a neural network. And nowadays, we deal a lot of problems, and it can actually be solved. Just change the tuning parameter. Um, there's no guarantee that it will work given the new data set, but it is one way to perhaps make your model better fit. So let's jump ahead to, I believe the concentration of this paper, which is this weight space transformation. It's actually a lot of linear algebra. So I'm just going to briefly cover that part. I think the good thing to start, which is weight sharing. Weight sharing consists in having several connections or links be controlled by single parameter or weight. Weight sharing can be interpreted as imposing equality constraints among the connection strength. The interesting feature of weight sharing is that it can be implemented with very little computational overhead. I think today all of this stuff is handled in the package. You don't actually have to go completely out of your way to manipulate the weight, manipulate the structure. But the good thing to keep in mind when you're reading this line of the paper, which is we're talking about 30 years ago, right? Um, First of all, this is not easy 30 years ago, and the second of all, uh, the computation cost it's so high that it is very difficult and challenge to come up with the hidden intrinsic weight space to further to allow people to understand truly what's going on when you have these abstract structure. And I think typically people rely on looking at the performance and then say, okay, if this structure is good or bad. Um, but I think uh, but I think the key here to understand is the computational cost and speed. So those things are definitely good information to keep in mind. Now, the second thing that's important about this paper is the general weight space transformation. And I believe the highlight is a process, a connection strength can be computed from the parameters to a given transformation and provided that the Jacobian matrix of this transformation is known so that we are able to compute partial of the cost function with respect to the parameters. The gradient of the cost function with respect to the parameters is then just the product of the Jacobian matrix of the transformation by the gradient with respect to the connection strength. Um, and the situation can be seen in figure 1, which is here. Now, I actually don't think this figure is completely transparent, to be honest, especially for somebody who don't really have the education in linear algebra. Specifically, take myself as an example. When I first read this paper, I actually don't think I'm very good at linear algebra. I know maybe a few basic things. So it posed quite a challenge. So I would say that the key here to understand this part is, first of all, there's this big concept of gradient descent, which is a procedure that's iteratively taking steps to searching for the optimal weight. Each step you update it, hopefully you get closer and closer to your target, the target which is your loss function or your cost function. And um, and I think the discussion here is really trying to come up and is really trying to say, okay, it is totally possible that if we do this, we are able to find that optimal point, which back in the days, it's difficult to see that's true, to be honest. Considering if your degree of freedom is in the thousands or tens of thousands, then it's going to be very difficult to see. But I think the key here is really the search for the optimal parameters. So here we're gonna put a mark, and we're gonna say this is the search for optimal parameters. Okay. you have some sort of cost function. Maybe you have a y that's your ground truth, and then maybe that's y hat that's your educated guess. And then you can take gradients, right? And then the gradient descent, which is update your weight every time by the previous step weight. If you're gonna know that as I, then that's gonna be I plus one plus some sort of gradient, which is compute from here. And this weight we want to know, it is important. So here we're gonna say it is important to know the search may be successful. And people need to have that hope, right? We need to have that hope before we go out of our way, go into the computer lab, and start an algorithm that might take 5 days. So that's going to be extremely important. Here are some math formula. These are just linear algebra. That's how you combine it. C is the cost function, and this H is a Hessian matrix. Um, and and this W, I believe nowadays people just call it weight, but I think in this paper they call it the connection strength. And then there's going to be a lambda, that's diagonalized version of this Hessian matrix. And then they also denote this Q, which is a unitary matrix formed by the eigenvectors of the Hessian matrix. And then altogether, this cost function is going to be transformed from here all the way to here, which takes this giant form. Now, this might look confusing, right? But then they use the notation U as the matrix multiplication as sigma QW, and then they can essentially replace this part by U transpose and U, which notation-wise is a little bit easier. And this part is also U, this is U transpose, and altogether you can rewrite your cost function using just U and J and K. And then after the definition of the cost function, then we can pursue to the next step, which is to find the optimal solution, right? So here we got a little discussion of how to find the optimal solution. Let's write that down. How to find optimal solution. And then perhaps you can use gradient descent, or you can use Newton's method, right? So either these two ways is fine and can allow you to search for the optimal parameters along the global parameter space. So that's going to be the big picture, the theoretical framework provided in the paper. And with that being said, we can take a look at examples. So before we hit on example, the key word here to wrap this theoretical discussion up is that this WST just described above is an example of problem-independent WST. And there are, of course, other sorts, right, that are problem-dependent, which can be devised. So in other words, they're really trying to give themselves a way out, right? They're not trying to say, oh yeah, this is the best structure, use it, you'll be good, right? In other words, if we can hit the problem independent, that's of course good. Then I can just use this one method, that's a set of parameters, and I'm done. Then it's great. But in reality, it's unlikely that's always the case. In reality, it's most likely problem dependent, right? It's problem dependent. If I have an input layer that's x1, x2, maybe all the way to x30, then I'm going to be passing into a neural network that perhaps has node 1 all the way to maybe just node 100, right? Then maybe that's going to be good enough. If I'm having x1 to x30, I'm not going to overkill to go completely crazy with this thing and give it like 100k nodes, right? That's probably overkill. You're probably going to be overfitting too many parameters. It's a lot of trouble, a lot of headache to train, to find the optimal parameters, and there's no guarantee that the solution will work well on the testing set. So the idea that this thing is problem dependent, I think it's going to be a very important leeway, not just in terms of writing paper, sell their paper, but also in terms of developing a whole field based on this idea. So this is going to be the grounding. So this is going to be the founding block for the field of flexible neural network. And I think the key here is going to be extremely important. Specifically, they're going to demonstrate for the rest of their paper how these architecture can be changed. For example, let's take a look at this small digit recognition problem. Um, Nowadays, we have a much larger data set. It's called MNIST. So that's going to be the buzzword used today. Back in the days, 1989, this is a very small data set. This MNIST, there are 60,000 pictures, and they're 28 by 28. So it's like 780 something. Specifically, I think this is going to be 784 pixels per image. It's not high resolution, right? It's not HD version, right? It's still very unclear. The pictures are handwritten. It's 28 pixel by 28 pixel. We're not talking about highly clear pictures, but even that minutes data set, comparing to what this paper is talking about, it's going to be a bigger size. And specifically in this paper, they're talking about a rather small data set. Let's take a look. The database is composed of 480 examples, numericals represented as 16 by 16. So in other words, one picture, it's a number, right? I write a digit, right? Maybe 8, something like that. And that's 16 by 16. So there are 16 pixels here, there are 16 pixels here. And then they talk about how they process that data. And then specifically, the training set is formed by choosing 33 examples for each class at random. And then the remaining 16 examples for each class were used as test set. So I would say that it's much less observation and it's much less insights. But hey, this is the beginning stage, right? We're taking a path down memory lane. If they can figure this out, who's to stop them from figuring out the minutes data? That's 60,000 images and 700 pixels, right? So it's going to be an important thing to start. This is the data. That's the picture. Each picture is size 16 by 16. So let's say I pick this one. That's going to be 16. And I pick this one. That's going to be 16. 16 by 16. That's the size. That's the size, you know. And then there are 10 digits, right? So if I want, I could call this class 1, class 2, all the way to class 10, right? It's like a 10 class classification. So the design of the neural network, in the end, you go through all your trouble. In the end, you probably want to have 10 of these, 1, 2, all the way to 10. And each of these nodes is like an output of some sort of activation function. I think you can just pick softmax, right? Here you can pick softmax, which is a name for the final layer that has multiple nodes. And whatever nodes with the greatest number indicates that observation is that class. If this number is the largest, then it's class 1. Okay, so then it's digit 0. So that's the overview of what the data looks like. And let's talk about experimental setup. Experimental setup is quite briefly described in very little notation, which me personally, I like it, but on the downside is that it takes some of the information away from the reader, that if you're just reading this without any computer code, it's going to be very difficult to appreciate the design and the intrinsic value contributed by the experimental setup. So I would say, if you're first time reading this paper, get your hands dirty, have a sense of computer code, kind of go through it. That will allow you to appreciate this paper much more, specifically this section of experimental setup. So we know we want to do background. Okay, that's where they did it. First of all, we have units. Nowadays, we call this neurons because, hey, you know, people want to sell their paper. That's the marketing strategy. Neurons is related to neuroscience, it's related to biological terminology. But in the old days, I think unit is perfectly fine. In the network, they have all these units. And first of all, it's a dot product between the input vector and the weight vector. So we're talking about something like this. x1, x2, x whatever, call that xp, and then you have a weight, right? Maybe that goes here, maybe that goes here, maybe that goes here, and then maybe you have w1, w2, and then maybe you have wp. Altogether, dot product means x1 times w1 plus x2 times w2 plus all the way to the end. XPWP. Now, this seems complicated, but usually people just write a summation j from 1 to p, and then xjwj. Altogether, you call that as some sort of a, the final value that you want to send into an activation function, right? So in other words, this is going to be the linearity part, the linear part, linearity. And then this f, right? Whatever this f is defined, right? This is the activation function. So that's the nonlinear part. So this f is going to be the nonlinear part. And here, specifically in this paper, they design it as this a squashing function that is scaled by some sort of tangent, right? So it looks something like that. I think nowadays this type of loss function is called tanh. So today in the package is called tanh. It's a basic activation function that you can use, and it has nonlinear component in it, and it converges your output of the dot product, the linear transformation, into a certain range, right? And you can further use this parameter a to squeeze it into like a certain range. So maybe the final output you can interpret a little better, right? So that's really the setup of what you need before you do backpropagation. And I think nowadays people call this the forward propagation, right? So if I may, this people call it forward propagation. So you have forward prop, you have back prop altogether. That's essentially how neural network learns. And that's the key and rudimentary component of neural network. And if you're gonna learn neural network, that's gonna be the first thing that you learn. So let's take a look at the next step. Next step is to compute this cost function. And specifically here, this d op is the desired output, right? So here we're gonna put a note here. This is say desired output, and then this x op is going to be simply whatever output coming out from the model, right? So this is output out of model. And then you can see this cost function is sort of like a square loss, right? It measures essentially how far you are, right? How far this model is at generating output from the desired output, right? So in other words, this d op, you can think of it as a label. If we're talking about this y label in your data, you can think of that as label, right? And this can be some sort of educated guess, right? So we're gonna say educated guess. Okay, now obviously the cost function is saying, okay, the higher the cost means your educated guess is poor, or maybe you're at the beginning stage of the training process, you're not very accurate, and then hopefully as we go through the gradient descent, many iterations, the cost is smaller, meaning your educated guess is more accurate. You're closer with the label. You pretty much look like what the real label is. And that means you're more accurate, you're good to go, you have a less mistakes, and maybe you stop there if you're happy with the error margin. And that pretty much finishes up how neural network learns. And I believe in the end, you can pretty much just use Newton's algorithm, or you can just use standard gradient descent, and that will get you to the most optimal parameters of your neural network structure. So this part, if I may, you can call it backprop. But I think this bracket is probably a little bit smaller. The accurate way is the rest of this portion of the paper. They together actually talk about backprop in total. So there you go, right? So you have a neural network design that looks like that. And then you go from left to right, that's forward. And then once you hit the end, you come back, that's backward. And you update the weight, right? This is one round going forward and one round going backward together. That's called one epoch. One epoch in today's terminology. And that's how I search for the optimal weights. And altogether, that's how neural network works. So as you can see, the design is very neat, very artistic, I would say. And that's going to be a standard gradient descent, I would say. You can, of course, use Newton's method. And there you go. That's how you train. That's the mathematical foundation. The first experiment that I did with this image data, 0, 1, 2, all the way to 9, is a single layer network. So this net 1 is a single layer. Specifically, it's fully connected. Oh, there you go. So that's the word, fully connected. That's the keyword that we use today. I think they brought this up in the beginning of this paper. That's quite early. With 10 sigmoid output units. And together, that's 2,570 weights. Also including the bias. And they throw data directly into the network, they train it, forward propagation, backward propagation. The results is not that bad, right? They're getting somewhere. 10 class classification, the random guessing is going to be 10%, right? I don't know which one of the 10 is the right one, right? So I'm randomly picking one. The humans will probably get like 99%. And specifically, this data is quite simple, 16 pixel by 16 pixel. So I would say humans should probably get to 100%. Unless like somebody is like making a lot of mistake or drunk, he might misnote one digit, 7 to 1, something like that. He might make one mistake, but that's it. You and I look at the data, we're gonna get 100%. So the idea is, okay, we have pictures, we have a design of neural network. Can we beat humans? You can't really beat it because it's already 100%. Can we perform close to human guesses? That's the idea, right? And initially, if you just have one layer, maybe you get something like 80% or 72% because the parameters are initialized with random draw. So you're not going to get the exact same prediction rate every experiment because the initialization is different. But if you repeat this experiment many, many times, you should be able to get a certain range that the prediction rate falls in. And you can talk about confidence interval or whatever, but then there should be a range about 72%, 80%. It's already a big jump from 10%, right? So in other words, here, one layer, net 1, we're going to get I'm gonna call 75%, right, or 76%. That's maybe like the middle ground. So that's already not that bad, right? From 10% to 76%, hey, we have a good starting point. And that's gonna be the performance chart. So as you can see, if the training epoch, we talk about this epoch, right? One forward, one backward, that's epoch. So epoch, we're gonna say one forward, one backward, that's one epoch. One epoch, you train, you update your weight, you calculate the output layer, there is a loss, right? There's a measure of mistake, right, from your cost function. And the reverse of the mistake, the other portion of the percentage of mistake is going to be your percentage of the correct guess, right, which is this correct guesses. And as you can see in the beginning, you get something like 60%, 70%, but then eventually you go up and net 1, it's this line. It goes up to a certain level, maybe 80%, and start going back down, maybe get to 72%, and maybe that's it, right? And then you get some sort of error margin. That's how volatile the performance path might be, and that pretty much is how good the performance is. So it's getting somewhere, it's not that bad, but then what they're saying here is if you increase the design from 1 layer to 2 layer to 3 layer to whatever layer, the performance gets higher and higher. Okay, gets higher and higher. Specifically, when you get to net 5, which I believe it's this line, then as you can see, almost hit 99%, 100%. And I would say that this is essentially where humans are, right? So human is probably there, right? So that's the big picture. I'm not going to bore you guys talk about how 1 layer or 2 layer works, but I do want to mention one small detail, which is in net 3 and can be seen in this picture. This is actually straightforward neural network. Same with the second one, straightforward neural network. It's just there are two hidden neural network layers. Now, here's an interesting thing that they did. Apparently, they already had this idea of convolution neural network when they're publishing this paper in 1989. I actually don't think this part was discussed in detail in this paper. I think this paper is focusing on backpropagation, and we can use linear algebra to explain how to set up this cost function, and we can use gradient descent to search for the optimal parameters. That's it, right? I think that's going to be the key point if I want to summarize this paper in one sentence. But reading this paper thoroughly, if you take a closer look, you actually get this sense that LeCun actually had this idea of convolution neural network when he published the paper neural network. So really what's going on here is there's a lab, right? Let's say I draw the world in two pieces. This is your lab, this is out there in the market. And when you publish in the market of neural network, he already done neural network. Obviously that's true, otherwise how do you publish it? Then he also has this idea of convolution neural network, which is not published in the market yet. No one knows about the details yet. So I think that's the key point here. It's like you're publishing a software package, right? When you sell the package, Microsoft Office 2010, then you probably have 2012 already developed. So it's the same idea here with them. That when they develop neural network, when they publish this paper, they already have the convolution idea in them. And that's what I really starting to appreciate the author and his team, which is because they had a plan. They had a vision, they had a plan, and they executed perfectly. So that's really the key point here. So let's take a look. Net3. Okay, what's the difference about Net3? Net3 talk about this. Since reducing the size of the network will also reduce its generality, some knowledge about the task will be necessary in order to preserve the network's ability to solve the problem. And again, missing a period. A simple solution to our over-parameterization problem can be found if we remember that the network should be recognized images. So specifically, the assumption here is image data. If it's in natural language processing, of course, today we use CNN, but back in the days when they published this paper, I think we need to be a little bit more careful of the form of data, which is essentially what they are trying to do here, which is to lay out the groundwork. Okay, right now we're trying to build something that's problem dependent, right? So here another keyword is problem dependent. And the problem here is image data. We want to recognize what's going on in the image data, right? If it's digit 1 or digit 9, we want to know what that is. So there's going to be some preliminary knowledge that we can borrow from the pictures. Okay, so let's see how they're doing it. Classical work in vision pattern recognition have demonstrated the advantage of extracting local features and combining them to form higher order features. We can easily build this knowledge into the network by forcing the hidden units to only combine local sources of information. The architecture comprises two hidden layers, namely H1 and H2. The first layer, H1, is a two-dimensional array of size 8 by 8. So let's take a look at the figure, right? This is a figure. And then there are three networks. Net 1, Net 2 is just neural network, but one more layer. Net 3 is what we just said, right? There's a convolution component in it. So what's happening? Net 3, this is the picture 16 by 16. And if you want to somehow shrink the size of 16 by 16 to something smaller, right? Say 8 by 8. Then what they're saying is, okay, each unit of H1 takes its input from 9 units on the input plane situated in a 3 by 3 square neighborhood. In other words, what they're really trying to say here is this. If this is 16, I'm going to be building up a 3 by 3 square. That's 3 by 3 square. And then each of these 3 by 3 square, I am somehow combining this information all together and turn that into one number. And I'm going to position that in a relatively similar spot, but on a much smaller scale. So what do I mean by that? So if this is 16, right? 16, and this is 3, so we're going to do minus 3 plus 1, and then over, I think the stride, there's a stride, which I don't think they use the word here. For units in layer H1 that are 1 unit apart, their respective fields are 2 pixels apart. Okay, so stride is 2. That's the keyword here. Okay, so what does that mean? If stride is 2, we need to divide it by 2, and then you end up plus 1, and you take the floor. This will give you 16 minus 3, so that's 13, plus 1, so that's 14. 14 divided by 2 plus 1, and you take the floor, that's going to be 8. And this 8 is going to be the size of your new dimension. So what the heck is going on here, right? The formula here is this. The side of old image minus window size, so this is window size, 3 by 3, this is window size, which is here, plus 1 over stride. Okay, stride is, they said that they're skipping 2 pixels, right? That's perhaps 3 by 3, and then the next one, when they rotate, they are really moving towards not here, but here. So 1, 2, so that's a stride of 2. So here, that's why you want to divide it by stride. And then plus 1, you take the floor, so this means floor. Floor basically means if you're 7.1, then it's 7. It's 7. And then if you're 8.1 floor, it's 8. And this is actually going to become the side of new picture. And that's the formula to convert 16 by 16 down to 8 by 8. So you're going to get a little bit shrinkage from here to here, and a little bit more shrinkage from 8 to 8 to 4 by 4. Now we have 4 by 4, right? 4 by 4 is 16. So we're essentially talking about a model with 16 features, right? We could work with that. That's not that many. 16 features, you're feeding into a neural network layer with 10 nodes, right? That's kind of nice, right? It's not that many parameters. We shrink the size. There's some sort of dimension reduction flavor in it, and perhaps there's a better performance. So here we're going to say another keyword is dimension reduction. And that's another keyword. So altogether, you can see that the design, the discussion of the entire LeNet 3, it's really focusing on how do you extract the information from the picture, and then you do neural network, right? So in other words, let me summarize. Net 1 and 2 are both about building deeper neural network. However, Net 3, it's really about extracting features from image and then build neural network. So it took one more step, but this step is not expanded and discussed in great details for outside reader, right? What do I mean by not in greater detail? Today we're talking about all kinds of filters, right? There are filters that look like this. There are filters that look like this, right? All these smaller window can be artificially designed, and you can apply that on the original, perhaps 16 by 16 pixel size images. And each of this will extract different information out of the original picture, right? Say if this person is my father, right? Let's say that's my father, and that's his eyes, that's his nose, that's his mouth. Maybe his eyes look a certain way, okay? And I want to have some sort of filter that only attract the size area, so the middle is all 1, everywhere else are zeros. Then if I take this filter and happen to stumble upon this area, then I can get a feature that's the person's eyes, right? And this eyes is going to be an important feature lots of information packed together, right? They're not sparse, right? They're not pixels, right? They're condensed information, right? Altogether gives me a new feature, eyes, right? So this is going to be eyes. And use the eyes as the input layer for neural network. And that perhaps is going to be much more informative. And that's really the direction that they're trying to take. So in the end, there's going to be much more design. For example, Net 4, Net 5, they can really expand this way, right? That's the width of the convolution layer, or they can increase this way, right? That's the depth of convolution layer, right? The width and the depth. So obviously, all these are tuning parameters. So they are tuning parameters, right? There is width and there is depth, width and depth. And all these are tuning parameters that you can play around with, and perhaps it will land on much better fit simply because your model is more tuned towards the real shape of the data. And then we can come back up to look at this performance again, and you will have a new appreciation for what's going on in this performance chart, right? As your net goes more and more complex, right? And essentially, what you observe here is a complexity. So maybe this is easier, and maybe this is harder, right? In terms of complexity. And as you can see, as complexity increases in the design of the neural network, then the idea is, okay, maybe it's more tuned towards how data look like, it's better fit, and therefore it has higher performance. Here, maybe you're going to get 99%, 99.9%, something like that. So there you go. I hope this paper is a detailed introduction of what I'm reading when I just started to learn neural network. And that's going to be the foundational step of artificial intelligence. So I hope you enjoyed the paper. If you do, give a like, click that subscribe button, and I'll see you in the next episode.